Hello everyone, welcome back. Let's talk about another hard problem on Leetcode today, height of binary tree after subtree removal queries. In this problem, we are given the root of a binary tree with n nodes. Each node is assigned a unique value from 1 to n, and we are also given an array called queries of size m. We have to perform m independent queries on the tree, where in the ith query, we do the following. Remove the subtree rooted at the node with value queries I from the tree. It is guaranteed that queries I will not be equal to the value of the root. Then we should return an answer array of size m, where answer I is the height of the tree after performing the ith query. Again, as a note, the queries are independent, so the tree returns to its initial state after each query. The height of a tree is number of edges in the longest simple path from the root to some node in the tree. Then in example 1, for the given tree, only query given to us is 4. That means we can remove node 4 from the tree and we will get the tree like this. And in this case, the height of the tree will become 2 because we count number of edges in the longest simplest path. So because of this, the height of the tree is 2. And in this case, there was only one query. So we will return the array of size 1 with 2 as our answer. Now let's see example 2, where we will understand what do they mean by independent queries. Here the query nodes given to us are 3, 2, 4 and 8. And when we remove node 3, the height of the tree will be 3, as we can choose this longest path or this one. So because of this, we return 3 for it. Now because our queries are independent, our tree reverts to initial given state. And now the query is 2. So we get rid of subtree rooted at node 2. That is, we get rid of node 2 and its children 4 and 6 as well. So now the height of the tree will be 2. It can be from this path or this path or this path, right? So we will return true in this case. Now we revert the tree to initial state and process the query 4. So we remove node 4 and this time the height of the tree stays 3 starting from node 5 till node 6. And finally we revert the tree again and go to query 8 and get rid of this node. So this will remove the subtree rooted at node 8. Now the height will be 2 coming from this path or this path. And now we will return all of these heights for all the queries. So we will return answer as 3232. Now in terms of solution, a straightforward approach would be to involve recalculating the tree's height from scratch after each subtree removal. So this involves following steps. First, we remove the subtree rooted on the specified label. For example, here it was 4. And then recalculate the height of the modified tree using depth first search or DFS. But this will be an inefficient approach because for m queries, we are running the DFS again and again, and the DFS time complexity will be O of n in the worst case because we are going through each node in the tree and try to calculate the height. So because of this, the time complexity is O of m into n. And now the question is, can we do better? And the answer is yes. This solution is inefficient because we are recalculating the height of the entire tree for each query. So instead of that, can we somehow pre-compute the tree's height with and without specific subtrees so that when we run the queries again, our time for each query reduces from O of n to something better. So when we calculate the height of the tree, the time complexity will anyways be O of n. And in any case, we have to calculate the height of the tree. But we have to do it smartly. And for that, let's look at binary tree node a bit closely. Each node in a binary tree has a depth and height, and the longest path or longest height passing through it is sum of these two values, that is depth plus height. For example, for node 4, depth is 2 and height is 2. So that's why the longest path passing through node 4 is 4. Similarly, for node 7, depth is 2 and height is 1. And the longest height passing through node 7 is 2 plus 1, that is 3. And now suppose in our query, we have a node 4 that has to be removed. That means we have to remove also its children's or the subtree rooted at node 4, stopping all the paths passing through it. However, if the node has peers, that is siblings or cousins, then the paths passing through these nodes will be longer than the path which was passing through node 4 because this node 4 now no longer exists in the tree. So now our task is reduced to finding that peer through which passes the greatest height. For example, for node 4 that peer is 7 because if we remove node 4, the height of the tree will be 3 passing through node 7, while other peers like 5 and 6 will result in height of 2. So how about when we are doing the DFS to find the height of the tree, We calculate the height and depth of each node in the tree. And then we group these nodes by depth because then we can access these pairs easily. For example, for the given tree, node 1 has height equal to 4 and depth equal to 0. Similarly, node 2 and 3 have depth equal to 1 and height equal to 3 and 2 respectively. Then node 4, 5, 6 and 7 have depth equal to 2 and node 4 has height equal to 2 and node 7 has height equal to 1. And both node 5 and 6 have height equal to 0 because they are leaf nodes. Similarly, node 9, 10 and 11 also have height equal to 0. And then for node 8, height is 1 and 8, 9, 10 are on the depth equal to 3. And finally, only node 11 is on depth equal to 4. Now let's group these nodes by depth because we know that all the pairs exist on the same depth, and if we remove one of the pair, the longest path still passes through one of the other pairs in the tree. So for depth 0 we will have node 1, then for depth 1 we will have node 2 and 3, for depth 2 we will have node 4, 5, 6 and 7, for depth 3 we will have node 8, 9 and 10, and finally at depth 4 we will have node 11. Now because our query has node 4, if we delete that node, its pairs are 5, 6 and 7. Now we know that longest height will be passing through node 5, 6 or 7. So now we can loop on these pairs, and for each pair we have already calculated depth and height. And if we sum them up, we will get the longest path passing through that node, and maximum among them will be the height of the tree. For example, for node 5 and 6, height is 0 and depth is 2. So the longest path going through node 5 and 6 will be 2. But for node 7, height is 1 and depth is 2. So the longest path going through node 7 will be 3 and it is the maximum. So the tree height will be equal to 3. So this way we can actually solve the problem. But finding this maximum again may result in time complexity of O of n, because in the worst case, at a particular depth, number of nodes may be proportional to number of nodes in the tree, that is n. So for each query, if we try to calculate the longest path among the pair list, that may again result in time complexity of O of m into n. And now the question is, do we really need to store all the pairs by depth? And the answer is no. Instead of keeping all the pairs, we only need to retain top two nodes with the greatest heights at each depth level. Consider node 4. If we delete it, we only need the maximum height value apart from node 4, which is node 7. Similarly, if query contains node 7, that is, we have to remove node 7, the pair we need is node 4. If node 5 is deleted, for example, and we can see that it is not on the longest or second longest path in the tree, the height of the tree remains same, that is, passing through node 4. So to optimize this, we just need top two pairs sorted by height for each depth. This way, even if the query contains a node resulting in the longest path of the tree, we can still get the second maximum path passing through the pair of the query node. Now there are multiple ways to achieve it. One way can be that we create a list of size 2 and keep it sorted. Another way can be we use a min heap of size 2, maintaining two nodes with the largest height. So now to get the maximum value from this list, instead of getting the time complexity of O of n, we will get a constant time complexity. For example, if we use a list and keep it sorted, the time complexity there will be 2 log 2. Because if we sort a list with n elements, that takes n log n, and here there are only 2 elements. Now let's see the updated peer list. For depth 0, there is only node 1, and then for depth 1, we have node 2 and 3. And earlier at depth 2, we had node 4, 5, 6 and 7, but now we only need node 4 and 7, sorted by heights. Similarly, at depth 3, earlier we had nodes 8, 9 and 10, but now we only retain 8 and 9. And finally at depth 4, we only have node 11. So now, if we delete node 4, only other pair it has is 7. So we will add the depth and height of node 7 to get the height of the tree. And in this case, it will be 3. And finally, there may be a case when there is only one node at a depth, and in that case the pair will not exist. For example, consider node 11. So the longest path was passing through that node, but after removing that node, now the longest path will be depth minus 1. That is one depth above the depth of the node that was deleted. So in this case, the height will be 3, for example. Now we can jump into the code part. First, let's run the DFS to compute the depth and height of all the nodes. And we will start from the root node and with depth equal to 0. Let's also define two maps to store depth and height of each node, where key will be the node value and value will be the depth or height depending on the map. And in this problem, we are given that all the values in the tree are unique. So that's why we can use node value as a key in the hash maps. Let's quickly write this function. So this function takes node and corresponding depth and returns the height of the node after running the DFS. If the node is null, then we will return -1 because there is no further subtree to process. First, let's store node's value along with its depth in the node depths map. Now we can calculate the height by first calculating the left height, where we can recursively call the same function and pass in the left node. And now as we go down, the depth increases by 1. So we will pass depth plus 1 here. Similarly, we will do the same thing for the right height as well. And based on this, we can calculate the height of this node as 1 plus maximum of left height or right height. We add 1 here because as it is a non-null node, it will contribute 1 edge to the height apart from the maximum height of left or right subtree. And then we will save the height of the current node in the node heights map. And now we can return this height. So now node depths and node heights both have node values with the corresponding depths and heights. Now we have to group these nodes by their depths. And for that, we can again use a hash map where key will be the depth and value will be list of nodes. And here I'm using list of integer array because then along with the node value, I can also store node's height and avoid recomputation of height again and again. And let's call this hash map peers because it is storing two peers for each depth or level with the highest height. For that, we will go through each node entry in the node depths map. And in Java, one of the ways to iterate on the map is using entry set. For each entry, we will get the node value and its corresponding depth. Now for each depth, we will initialize a list if it is not already present. And then we can get that list to add the peers to it. And now we can add node's height and its value to the list. And we can use node heights map to get the height of the node. And once that is done, we can just sort this array in the descending order. That is, bigger height should come before smaller heights. And now if the size of the array is more than 2, then we should get rid of the node with the smallest height. And that will be at the end of the array because the array is in the descending order. And because we are using the array list, we can get to the last index in O of 1 time by using the index peer list size -1 or index 2 itself because we are not letting the list go beyond the size of 2. So once this iteration is over, we can now calculate the result. Now we can just go through each query. Let's also define query's length here and use it everywhere. First, let's get the node value from the queries. Let's also get corresponding depth of this node and that we can get from node depths map. Now we will get the list of peers for this depth and that we will get from the peers map. Now we have three cases possible. If there is only one peer at this depth and that has to be removed, then the longest remaining path in the tree will be depth -1. Or if the queried node has the largest height among the peers, then the longest path in the tree will go through peer with second largest height at that depth, which is stored at index 1. And that longest path will be equal to height of the second peer plus current depth. Otherwise, if we are here, that means this node was not part of the longest path in the tree. So we can take the pair with the largest height, that is pair stored at index 0, and add current depth to its height. And finally, we will return this result as our answer. Now let's run this code. Looks like I forgot this angled bracket. And this should be node depths. And here the iterator should be I, not Q. Now let's run this code again. Let's submit this code. Cool. In terms of time complexity, it will be O of n plus m, where n is the number of nodes in the tree and m is number of queries, because first we are doing this DFS, which takes O of n time. And then again, we are going through this node depths map, which again has n elements in it. So because of this, again, the time complexity is O of n. But then when we are going through queries, there are only 2 peers for each step. So because of this, the time complexity reduces to O of 1 for each query, but we are running m queries. So because of this, the time complexity will be O of m and overall time complexity will be O of n plus m. And in terms of space complexity, it will be O of n plus m. Again, we are storing node depths, node heights, and then we are also storing peers for each depth. So because of this, the space complexity was O of n. And then we are using this result array to store result from m queries that takes O of m space. So overall, the space complexity is O of n plus m. So I hope this video was useful to you. If it was, please like, share and subscribe. The code link is in the description below. If you have any questions or suggestions, please write them in the comment box. Thanks for watching. See you next time.